thought I'd take a look at this WNT 200 device. I purchased it via eBay from a seller, Power 116, and it's described as a 50 to 200 megahertz universal serial bus sweeper signal source and RF power meter. When NWT4 is not a part of this package. And this thing cost $100. It was the seller intended to include, or said he did, these 2 cables and 2 adapters, but he didn't. I furnished them myself. There was a USB-A to USB-B cable, very nice cable, included in the package. So it's this metal box and the USB cable for $100. You may be able to read this. I can't. I did determine that these 2 BNC connectors, this one is out and this one is in. I'm going to turn it upside down here. The input, although there is I believe an isolation capacitor here, is not preceded by anything. This BNC connector goes directly to this chip. Chip is an AD8307, and that's a wideband power meter. So this is not a tuned input. Any RF signal that's fed in here between a very low frequency and 200 megahertz anyway, or 2 of them or 3 of them on different frequencies in the range, the power will be read by this chip and output. So this thing does not discriminate between frequencies. It's just a total power measuring device. This chip, I believe, is the oscillator. It's an AD9951. This chip provides a pretty nice sine wave output from some low frequency up to 200 megahertz. And the level's been adjusted to be about 0 dB here. That 0 dB signal is fed into 3 optional attenuators. By optional, I mean they can be turned on and off individually. And they are a 10 dB, a 20 dB, and another 20 dB. So that gives me 10, 20, 30, 40, or 50 dB of attenuation, depending on whether there's 1, 2, 3, etc. That goes to the output. This oscillator can be configured to provide a single discrete frequency between 50 or 100 kilohertz up to 200 megahertz. It can also be set to provide a frequency that starts at some low frequency, scans to some high frequency, jumps back to the low frequency, scans again to the high frequency. The maximum scan is 50 or 100 kilohertz to 200 megahertz. There's a PIC 16F876A processor and an FTDI interface chip, that is to interface the USB signal with the microprocessor signal. Now remember, this is an FT232 chip. This unit is not standalone. It's powered by the USB connector, and there is a program required. I use a Windows version. I know there's also a Linux version. I don't know about Windows. The software I'm using is Win NWT 5. There is also a Win NWT 4 version available by a separate author. This whole type of device and the software was developed by a German fellow, and he did it open sourced. Well, the Chinese latched onto that and made variations and whatever. The original author no longer, as near as I can tell, offers an English version of Win NWT 4. And there's a bunch of places on the internet where they offer to provide you with a download of NWT 4. I've had problems with a lot of those places. Win NWT 5 by this fellow, who I believe this is the amateur radio call sign associated with this name, but I'm not fluent in Russian either. This software is available at this website, and I have a copy. It's just one executable copy, one executable file needed on my site, which will be linked down below. Depending on what version of Windows you have, and by what version I mean Windows 10, but it's been around for, 10 years almost? You may have to download an FTDI interface. And if you do, go to FTDI's site and download the virtual version. What that does is creates a virtual COM port on your computer and assigns it to whatever USB input you're using. Here is Win NWT 5 running on my laptop. You'll notice it's COM 3 and it's closed right now. I'm going to plug the USB cable into the device. And we'll see that COM 3 is opened. I'm going to connect the output and input together. I'm going to set the start frequency to 100 kilohertz. I'll set the stop frequency to 200 megahertz. And I'll do a single sweep. Now see what's happening. We're drawing a graph on the left hand window. And you see what happens. It drops off almost to minus 35 decibels at 200 megahertz. Now, I thought I could calibrate it to flatten that drop off, but I don't seem able to do that. At least I don't understand how to do it at this time. But let's set the frequency to stop at 100 megahertz. And I'll do a single sweep. So, with a simple loop back, the output to the input, and a span of 100 kilohertz to 100 megahertz, you'll see that there's about 3 dB difference. It drops continuously. Now I have a 10 megahertz band pass filter. I got this at AliExpress. It cost about $3. I'll insert this between the output and the input. And I'll do another single sweep. See, a typical bandpass filter doesn't appear to be centered on 10 megahertz, with some wigglies down here, starting about 40 megahertz on up. I think that the frequency of things happening above 40 megahertz are due to the fact that there's a total lack of shielding between stages of this filter. But let's set the upper frequency to 40 megahertz. And I'll do a single sweep. We have a pretty nice bandpass filter, but it's nowhere near 10 megahertz. I would say the center of that filter is about 6.5 megahertz. Turn the unit over and I see a note here that there's a DDS clock 600001320. I had no idea what that meant, but I found a place under setup that I could enter a DDS clock. So I have entered the number that was on the back of this device, and I'm going to say OK, and then I'll run a single sweep again, and look at what happens. The 1 megahertz blip is exactly at 1 megahertz. I've now got a 40 megahertz crystal hooked up. And I'll do a single sweep. And this is much more satisfactory. This is exactly what I would expect. Connect the bandpass filter from output to input. I'll set a start frequency of 1 megahertz. And a stop frequency of, say, 20 megahertz. And I'll do a single pass. Now this is a much nicer bandpass filter. We'll lower this to 100 kilohertz and raise this to, say, 40 megahertz. We'll do a single sweep. That's a much better. I rummaged around in my junk box and I came up with this. It's labeled 70 megahertz filter and equalizer. It's got a SMA here, an SMA jumper, here and here. And if we look at the underside of it, there's apparently it's in two parts. This looks tremendously like a bandpass filter arrangement. So I think what I'm going to do is take off this SMA jumper, because if this truly is a filter and equalizer, this might be an equalizer. I don't know what that means. There's no power connection to this thing. It's totally passive. I'm going to assume that this is the input for no better reason. I'm going to see if this is the output. I'm going to hook the 70 megahertz bandpass filter up. Or filter, I don't know, it's for sure a bandpass filter. We'll start at 10 megahertz and stop at 125. Give it a single sweep. Now that's a nice 70 megahertz bandpass filter. You can see the two cursors have moved here and here, which would be about 55 to 83 megahertz. So it is a 70 megahertz bandpass filter. Here we see where the Win NWT5 was developed by first the developer of Win NT4 and second the developer of Win NT5. And you see here is the original Win NT 2, 3, and 4. I don't know if it was a 1 or not. DL4 JAL. And here's this Andy Sobel, who wrote version 5 in 2015. I think I'll look some more at that. I'm going to try to put an amplifier across the in and out terminals. It does caution me that if I'm going to connect an amplifier to it, it says the network tester can handle approximately 10 dB input. So when the output is to be measured, it's going to require an attenuator before it goes into the input. And I can enter the value of that attenuator in this box, and it apparently will rescale the vertical axis to allow for an additional attenuation. Now that is not including attenuators here, which attenuate the output. So I'll wrap this up and then come back with some amplifiers, maybe.